All right. Hi, welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development and serves a global membership of computing professionals and students. My name is Peter Van Hardenberg. I'm the research director at Ink and Switch, an independent research lab that studies tools for thought. I've worked in software development for about 20 years with an industry background that ranges from building games for Game Boys all the way through cloud platforms. And I've been collaborating with Martin now for about 5 years. So I'm really pleased to get the opportunity to host this session with him. For those of you who are not familiar with the ACM, here's a little bit about them. The ACM offers educational and professional development resources that can bolster your skills and enhance career opportunities. You can see some of those highlights on your screen. The ACM provides access to the ACM Digital Library. That's the world's most comprehensive database of computing literature. Had leading publications and global conferences that draw top experts on a broad spectrum of computing topics, and supports education and research, including curriculum development, teacher training, and offering the ACM Turing and ACM Prize in Computing Awards. And of course, the ACM Code of Ethics, which is a collection of principles and guidelines that are designed to help computing professionals like you make ethically responsible decisions in your professional practice. Now, before we get started, we'd like to mention a few housekeeping items on the slide you see here. First, if you have any questions at any time, please use the Q&A button. We will organize the questions as Martin speaks, and we'll get to as many as possible. If something is confusing or unclear, please feel free to ask for clarification. I'll try and keep an eye on the Q&A as we're going, and we'll save most questions for the end, but if there's something that maybe could use just a quick clarification, we'll do that. Also, the session is being recorded and will be archived, and you'll get an email notification when the recording is up. And of course, you can always check learning.acm.org for updates on this or any other upcoming webcasts. Last, at the end of the presentation, you'll get a survey on your screen. We would definitely appreciate it if you would take a moment to fill it out and help us improve future Tech Talks. Okay, now, today's presentation is Creating Local First Collaboration Software with Automerge by Martin Kleppmann. Martin is a research fellow at TU Munich in Germany. He was previously a research fellow at the University of Cambridge, and he is the author of the best-selling O'Reilly book, Designing Data-Intensive Applications. He works on distributed systems and security, and in particular, CRDTs, which we will define, I'm sure, in a moment, with end-to-end encryption. In a past life, Martin was a software engineer and an entrepreneur, co-founding and selling 2 startups, and worked on large-scale data infrastructure at LinkedIn. Okay, with no further ado, Martin, please take it away.
Thank you so much, Peter. Okay, so my slides should be up. Yeah, it's great that you can all be here. I would like to talk today about local first, collaboration software, and Automerge. Don't worry if you have never heard of either of those things before. I will explain what I mean with them in a moment. So let's start with the idea of how web apps have been developed over the ages. So if you think back, maybe in the olden days, the days of classic web apps, you would have a server that you would write in PHP or Ruby or whatever, and it would return some HTML to a web browser. The web browser would render it. When the user wants to enter some data, they would fill in a form and submit it, and it goes back to the server, and the server would store things in a database. And, it works, but of course, as you well know, web browsers have become much more powerful, and web apps have become much richer over the time. And so the common architecture that is used for many web apps now is that actually it's a single page. There's a lot of JavaScript side, client-side code that is actually making HTTP requests to the browser and fetching some JSON and then rendering it client-side. And of course, Google Docs and the various similar collaborative editing tools are built this way, including modern ones like Figma, project management tools like Trello, and so on. It has given us great features, but also it has brought a lot of complexity to build applications this way. If you think about just all of the layers of data that are involved in a single page web app, first of all, well, you've got the web browser displaying the data, and so the data is manipulated as a DOM using the HTML DOM, manipulated using JavaScript in the web browser. And the web browser and this JavaScript will have its own application state, which it might manage just using regular objects or maybe some kind of client-side state framework. And that state then gets rendered into the user interface, maybe using a library such as React. But then that client-side application has to be somehow synchronized with the server. And so there's also probably a REST API through which the client then talks to the server, makes requests there, takes the data that's returned from the server and updates its client-side state, which is then rendered into the user interface using something like React. But then if you think about it from the server's point of view, well, that REST API has to be implemented somewhere. So probably there's going to be some model objects that take the requests from your REST API, turn it into something meaningful from the application side on the server, and then those model objects have to be turned back into JSON objects in order to be returned through the REST API. But those model objects, well, they have to be stored somewhere. So probably there's some kind of object relational mapping layer in which you can then allows you to store those model objects in a database. And the database itself is then some kind of data model, maybe using SQL or maybe some other data model, which is in turn then built on some sort of persistent storage. And if you think about it, there's just so many layers here, and layers, and most of the code in the application is just transferring data from one representation into another. And we're just pumping data through all of these layers, but most of the code is not doing anything interesting. It's just converting from one representation to another. And this is kind of tragic. But it doesn't stop there. There are even further problems with the way we build web apps nowadays. And another one is the following. So let's say, okay, you've built a nice shiny web app. The user hits a button to do something. Some JavaScript event handler fires to handle that button click. And as a result, you need to store some data on the server. Okay, so, well, you make an HTTP request to the server. At some point, that request arrives at the server. Some server-side code handles that request, maybe makes some database queries in order to store the data. And then what happens on the client side in the meantime? Well, the client is just waiting for the server's response to come back, So it's showing a spinner, spinning. And at some point, finally, the HTTP response comes back from the server, hits some callback function in the JavaScript app, and now you can update the user interface to say, yes, okay, it was all done. Okay, so this is kind of painful because, you've got the user just sitting there waiting on the spinner. So some people had this genius idea of, well, what if we just update the user interface immediately? And just immediately when the user clicks the button, we just say, yes, okay, even though the HTTP request hasn't actually completed yet. But we're just going to say it's okay, and we're going to call this optimistic UI. And we're just optimistically going to update the UI to say it's all fine. And then at some point later, the request will complete. But the problem with this is, well, what if not everything is fine? Because it might be that the user is actually sitting on an unreliable coffee shop Wi-Fi, and that coffee shop Wi-Fi just decides to let you down. It's having a bad day. Sorry, Wi-Fi is overloaded. That request never got through. Or maybe the request got through and the response didn't get through. But for whatever reason, eventually the request times out. And now you're kind of in a stupid situation because you've already updated the user interface to say everything is okay. Now you have to kind of retroactively go back and fix it up and say, actually, sorry, we lied to you. It was not okay after all. Your data was not saved. If you close your web browser tab, all of the data is going to be gone. So sorry about that. Please try again later. As a response to all of this, my colleagues and I came up with this concept of local first software, which you can read about in this article at the URL here, but which I also want to explain to you now. So if I had to summarize the way how state management works in traditional web apps, it's basically the only authoritative data storage is on the server. If you have some data somewhere in the system that is not stored in the server database, then basically it didn't happen. The only way how something becomes permanent is that it's stored in the server's database, which of course means that if you can't reach the server right now because, say, you're offline, well, sorry, you can't actually do anything. Now, the local first model just inverts the priorities and says, we still have servers, we still have clients. On the high level, not much has changed, but we changed the priority order of the storage and say, rather than saying that the server storage is the primary storage and the only thing that counts. We're going to say the client has local storage as well. It's a device, it has a hard drive, we can store data persistently on the client. And we're going to say in local first software, that local storage on the client is where data gets stored first, and it's the most important place where data gets stored. There might also be some servers involved, but they are really in a secondary role. They serve as a synchronization mechanism so that the data can get from one user to another, and they serve as a kind of backup mechanism in case you lose your device. But the primary storage is really what happens on the client. And this change of priorities turns out to actually just fundamentally change the development model. Because, for example, it doesn't matter if you're offline or online right now, because your local data storage on your own device is always available regardless of the status of your internet connection. And so that means now if the user hits the button to do something, the JavaScript event handler can fire, it can store the data locally in the local storage on the user's device, and it can immediately update the user interface to say, okay, and it's true. In this case, it's not a lie. It's true that the data has been stored correctly because it's been stored in the place that matters, which is the client. And then in the background, there's a synchronization process that takes that data that has been written and syncs it to the server and to any other users who are collaborating on that piece of data. But the important thing is that we've now moved the sync to be a background process rather than synchronously something that the application has to wait on. And moreover, in this pile of chaos here that I talked you through earlier, if we adopt this local first approach, we can actually radically cut down the number of layers of data conversion that we have to do. Because you actually just have to think about the client-side web app, because you still have the application locally on the client running, for example, in JavaScript in the user's web browser, but it only needs to talk to local data storage, and it can use a library for that. And moreover, all of the data synchronization process also, that's not application code. That is library code that you can just import. You can just use an off-the-shelf library to perform that data synchronization between a user and the servers and any other users. And so just in the way like you wouldn't implement your own database because Postgres is a perfectly suitable server-side database, there's no need for you to write your own database. In the same way with the local first model, there's no need for you to write your own data synchronization layer, because we can make a general purpose data synchronization layer that you can use for many types of apps. And then that allows you to just use that off-the-shelf piece of library code and not have to write that. Let's talk through a bit of the comparison between the traditional cloud software model and the local first model. And so one difference is the ease of building collaborative software with real-time collaboration. And so, that is possible in a server-side model, but it's kind of complex because a lot of the web frameworks don't really give you good support for real-time collaboration. They say, here's a WebSocket, have fun with it, figure out everything else yourself. And so this idea of like a user on one device updates something and syncing that with low latency to another user device, yes, you can do it, but it's kind of hard work. Whereas in local first software, that's built from the ground up to support this kind of real-time collaboration. But also, it's not just real-time collaboration while people are online, but also if users are offline, well, traditional web apps really don't work very well with offline. You can build stuff with service workers and so on, but again, it's kind of complex. Local first software is designed from the ground up to also work offline. What about the server? If the server goes away in traditional cloud software, well, your primary data storage is on the server. If the operator of the server goes out of business, say you're using some web app built by a startup, the startup runs out of cash, they turn off their AWS services, everything shuts down, and all of the data that was stored on those servers is now no longer accessible. Whereas in local first software, because the data is stored locally on the client's own device, that means nobody can take it away from you. You as the client have that data, even if the server goes away, at least you have a local copy that you can still use. And moreover, with the traditional cloud way of building things, there's all this complexity because you have to build all of these server-side infrastructure in addition to building your client-side web app. Whereas with local first software, as I said earlier, the idea is that we can build the synchronization infrastructure once as a general purpose library, and then everyone can use that same thing. And any servers that are involved, they can then just talk this general purpose synchronization protocol, and you don't have to write the servers for every single app. But hopefully we can get to the point where the same service can provide a syncing service for a whole range of different local first web apps. And so that way, in the same way as you wouldn't write your own Postgres, you also wouldn't write your own syncing service for a local first web app, because hopefully you can get a perfectly functional one off the shelf from somewhere. So those are the pros of local first software, but I don't want to present it, as somehow some magic thing that solves all problems, because of course, like with every tool, there's situations for which it's well served and situations in which it's a less good fit. And so I want to make that explicit as well. So local first software works really well in types of software where it's basically the user editing a file. And this could be, a text file, but it could also be a spreadsheet. It could be presentation software, it could be graphics software, video editing, whatever. When all those types of apps where basically a user can change the file in whatever way they want, that works really well for local first software. It also tends to work well for productivity software. So like note-taking and to-do lists and issue trackers, calendars, all those types of things. Again, they also have the characteristic that the user can update the data in whatever way they like. Like if it's a calendar, I can put whatever events in the calendar that I want. I can delete events from the calendar. Again, the data is under my control, and so therefore it makes sense for it also to be stored locally on my own device. Where local first software does not fit well is when it's an application requiring the management of some sort of real-world resource. So for example, if it's a bank account, well, in principle, I could have a copy of my bank account state on my own device, and I could update that in whatever way I like. But my bank is not going to care what updates I make to my local copy of the bank account statement, because what matters is the bank's copy of my account balance and not my local copy. So in this case, it makes sense for the bank to maintain the authoritative copy of the bank account balance. And so a local first approach doesn't really make any sense here. And the same applies to other physical resources. It doesn't make sense for me to edit the state of Amazon's stock keeping levels in their warehouse, because again, that's state for Amazon to manage, not for me to manage. So just make this clear, this is the type, the sort of left-hand column is the type of software that I'm talking about in this presentation. Okay, let me talk about Automerge, and let's make this more concrete and see how one might actually implement these kind of highfalutin ideas in practical software. So Automerge is a library that is intended to make it easy to implement local first software. And you can think of it a bit like a Git version control system, or a bit like a database. But so unlike Git, it stores JSON documents rather than just plain text files. And unlike a typical database, it lives in the client. And so the client can directly update the state of this data. And then Automerge provides a synchronization protocol with which any changes to that data can then be relayed to other users who also have a copy of this shared data. So as an example, I'll use a to-do list here. And so this is how you might represent a to-do list using JSON. And you can put this JSON in Automerge. And let's look at the manipulation that you might make. So if you want to change this JSON document, somehow you have to tell Automerge about the fact that you're making a change. And so you do that by calling the function automerge.change. This is the JavaScript API. And so you pass in the current state of an object, and you get back an updated version of the application state. And let's say, for example, we want to now indicate that the user has checked the checkbox on one of the items on the to-do list. And so I want to update the done field from false to true for the second item in the to-do list for watering the plants. And so the way I would do that is I call this automerge.change function, pass in the immutable state that the application had beforehand, and I get back an updated state. And within this callback here now, I can now perform arbitrary modifications to this, to the JSON document. I can also attach a human readable message to it if you want. You can have a sort like, think of it like a git commit message. It is just a human readable description of the change that was made, but that's optional. And then inside this callback here, you get a mutable version of the document, and you can just change it in whatever way you like. In this case, indexing into the to-dos array and setting the done field to true for that to-do item. Automerge then records exactly what change was made, and then provides a way of serializing that in such a way that you can save it to disk, and also that you can send it over the network to other users. Let's look at a different change. So for example, another user might also have a copy of this to-do list, and they want to add a new item to the to-do list. So here we want to add do laundry as a third item to the to-do list. And I can do that by just calling the JavaScript API doc.todos.push. .push is just a JavaScript function for appending an item to an array. And so it's just a straightforward API here to add this new item. Now, these edits that the user might make to this state, they might happen offline, of course. And we want to support users working offline. And so as a result, you might end up with different users ending up with slightly out-of-date versions of a document. Because here, for example, user A updated the document to say watering the plants has been done. And on a different device, another user independently added do laundry as a third item to the to-do list. And the whole point of Automerge is that it can merge these updates that happen independently from each other. It can automatically merge those back into a consistent state. And so in this case, the merged result is hopefully uncontroversial. Hopefully everyone would agree that the best desirable outcome in this case is that, well, watering plants has been set to true and doing laundry has been added as a third item. And we can just preserve both of those changes and merge them together and result in a to-do list that includes all of the changes from all of the users. Now, the key thing that Automerge can do is doing this kind of merging automatically. And I will explain to you in a moment how that works. But here I showed it to you with a JSON example. It can apply to other data types as well. So for example, you can also build a collaborative text editor using Automerge, or any application that's collaborative that involves text somewhere. So, if it's a presentation slide drawing app, that will have text on the slide somewhere, and each of one of those text objects you could regard as a collaborative text object in Automerge. And the way that text is represented in Automerge allows you to insert and delete characters anywhere within a string. And so, for example, let's say here we have two users which both start off with the document hello exclamation mark. The red user adds the word world before the exclamation mark, and independently on a different device, the blue user adds a smiley face after the exclamation mark. And again, Automerge can capture these changes that were made, and it can automatically merge those into a sensible final state. And that final state, hopefully you would agree, should be hello with world before the exclamation mark and a smiley face after the exclamation mark. So the way all of this works is that Automerge is something called a CRDT. This stands for conflict-free replicated data type. It's kind of a mouthful, but there's been a whole lot of research on the topic of CRDTs over the last 10 years or so. And the idea of CRDTs is that it allows different users to concurrently make changes to some shared data. All of those changes that are made are recorded as operations or as changes, and those changes can then be sent to each other. And when two users have seen the same set of operations or the same set of changes, then they must be in the same state, even if they actually got those changes in a different order. So for example, user A first applies their own change and then applies the changes it received from user B, whereas user B first applies user B's own changes and then applies the changes received from user A. And so now after the two have exchanged their edits, well, they've seen the changes in different orders, but they nevertheless converge to the same state. Moreover, this model actually supports not just real-time collaboration, but also sort of version control style branching and merging patterns. And so you can actually, for example, decide to deliberately go off on a branch and not merge changes in real time for a while so that you can work in private on a different version of some file. And then when you're ready, you can do a sort of pull request-like thing and allow the changes to be merged back into the main line. And you can, of course, have multiple of these branches side by side. You can actually compare what were the changes between one version and another. And all of these things are enabled by the change tracking that the Automerge CRDT needs to do anyway. So let me tell you a little bit about the implementation. So Automerge is implemented as a Rust library, and you can use it through a Rust API if you want. But the main reason for using Rust is that it's wonderfully portable to many different platforms. And so, for example, we compile it to WebAssembly and then have a JavaScript and TypeScript API that you can use to build web apps on top of Automerge. But you can also use it through a Go API, for example, which is in turn based on a C FFI API to Automerge. And if you're building mobile apps, you can use, for example, a Swift API or the Java/Android bindings And all of these are based on the same implementation of the same core data structures. So the idea is then you could build apps across whatever platforms you want to support, and they can all interoperate. So regardless of which platform the users are running on, they can all exchange the updates to the document, and they all share the same document state because they're all based on the same underlying implementation, same underlying data structures, and the same data formats. Automerge itself is just an in-memory data structure library. So it actually does nothing about storing data on disk or sending data over the network. But in order to do that, there's a companion library called Automerge Repo, which does that I/O. And so Automerge Repo then provides adapters for various options for storing on persistent storage. So for example, if you're running a native app on desktop, then you might be able to write directly to the file system. Whereas if you're in a web browser, you don't typically have access to the file system. So instead, you might write to a browser-provided storage API, such as IndexedDB instead. And all of these can just be plugged in. So the core Automerge doesn't care what you're using for storage. You can plug in any of these storage layers. And similarly, you can plug in a whole bunch of different networking layers. And whether you want to use WebSocket to a server or use WebRTC for a more peer-to-peer synchronization thing, or even just a plain TCP connection or whatever floats your boat, really, that can be plugged in there. So Automerge is independent of the actual networking layer that you use for syncing data between one device and another. A few words on the history of Automerge. So the project has actually been around for quite a few years, but for the first few years of its existence, it was really a research prototype. So we were using it for academic research and some industrial research to build some prototype collaboration apps and experimenting with the data structures and the behavior that we want, the merging behavior, and so on. But so over the last few years, it has then significantly professionalized. And so initially, for example, Automerge was super inefficient and just used a basic JSON-based data serialization format. But the file sizes you got there were huge. And so over the years, we then invested heavily in a compressed data format, which allows us to store all of that editing history in a very efficient way by compressing it using the custom compression algorithms. And at this point, we also introduced the sync protocol that Automerge is now based on. And so then in the last 2 years or so, we've made huge strides forwards. So initially, it was actually Automerge was implemented in JavaScript. But then last year, we moved to having the Rust implementation as being the primary one. And now all of the development is centered around the Rust implementation, and the JavaScript implementation is deprecated. That has allowed us to make huge improvements to performance. And we now consider the Rust implementation as being production ready as well. In particular, we have commercial sponsors, we have industrial sponsors who are supporting the development of the project through donations. And this allows us to have a full-time software engineer working on just making it good. So now it's no longer this random research project, which we're just a bunch of researchers are hacking on, but actually now it's a properly supported open source library. It's still totally open source, so there's no commercial product attached to this. The idea is really to enable anyone to build these kind of web apps. But if your company wants to sponsor this kind of thing, there is now a way how you can support the development of Automerge. And the very recent development has been that we've been adding new data types to Automerge. So in particular, we've been adding support for rich text, which I'll talk about for a few minutes after this. The Automerge repo library is quite a recent addition as well. And of course, we've been continuing to work on performance and such like as well. So in the remaining section I have on this talk, I thought I would tell you a little bit about the rich text data type, which we added to Automerge, just because it's kind of interesting and it gives you a bit of a glance into the types of processes that we've gone through while designing a library like Automerge. Because there's actually quite a lot of sort of design taste, I would say, that actually goes into this. Because if two users update some data concurrently, and we want to merge those together, there are often several choices about how that merge could behave. And what we want Automerge to be is sort of a well-chosen set of default merge resolution algorithms so that you don't have to think too hard about the merge. But just if you model your data in Automerge in the kind of obvious way, then hopefully you should get a sensible behavior out of it. And in the context of supporting rich text, so that is text with formatting like bold and italic, it turned out that actually using generic data types were not able to get the behavior that we wanted. And so we did this project called Peritext, which you can find more details about online, in which we designed a new CRDT algorithm specifically for handling rich text. And I won't run you through all the gory details of how it works, but I thought I would run you through the design process that we went through and some of the alternative designs that we considered and some of the problems with those alternatives. And that just shows some of the subtleties of actually building these kind of collaboration apps. So how should we represent rich text? And if you're familiar with building web browser-based apps, your first thought might be, well, make it a tree, obviously, because the DOM in a web browser is a tree. So that means you have a tree where at the top level you have an HTML document, and then inside that you have paragraphs. And then in each paragraph, if there's some words that are italic, then you will have an italic node as a node of this tree, and then any text that's italic appears within the italic node, and any text that's not italic appears outside of the italic node in the paragraph. And so here what could happen, for example, is you have this paragraph element containing the sentence, "the fox jumped," and two users start off in the same state containing whose document contains this paragraph. And now let's say that the user A wants to mark the word jumped as bold, and the user B concurrently wants to mark the word jumped as italic. And so, well, you would do that by creating a new bold and italic node respectively, adding the text jumped to the bold and to the italic node, and deleting the word jumped from the paragraph. Yeah, seems reasonable. Problem is, what happens if you now merge these two edits? Well, with most tree CRDTs, the behavior you will get is, well, it recorded, oh, we added a bold node, and we also added an italic node. Well, better keep both of those nodes. We added two nodes, we've got to keep both of them. And so the result is now that the document reads the fox jumped, once jumped in bold and another time once in italic. And this is not really what we wanted, right? We didn't want to duplicate the text. We just wanted to mark some text as bold and italic. So it's really weird that the text has become duplicated as an artifact of this algorithm. So this doesn't really seem to be a good representation of the data. Let's try a different representation. Let's try not representing it as a tree, but maybe instead representing it as markup. So in markup, you could use literally HTML markup with angle brackets, or you could just have some kind of special magic marker characters that indicate the start and end of a bold span. Doesn't really matter how you represent it physically, but the idea is that you have markers, marker characters that indicate here's the start of a bold, here's the end of a bold, here's the start of an italic, here's the end of an italic. Now, in this example, let's say we have the sentence, "the fox jumped over the dog," in which the first three words are bold and the last three words are non-bold. And now user A decides they want to unbold the whole text. And the way you would do this is by deleting the two marker characters, right? You delete the start bold from the beginning of the text and delete the end bold after jumped, and then you have achieved your desired effect of unbolding everything. User B, independently on a different device, wants to unbold only the word fox. And so in this case, the way you have to represent that is by adding a start bold character before fox and, adding an end bold before fox and adding a start bold after fox. And so that way, then you've achieved the desired effect of unbolding just the word fox. Now, what happens if we merge these edits together? Well, we've deleted the two original marker characters, and so they are gone. We've inserted two new marker characters before and after fox. So the end result now is that we have the end bold fox, start bold, jumped over the dog. So now, firstly, we have an end bold before a start bold. That's kind of weird, but okay, we could just ignore it and say that in this case, we ignore the end bold. Then everything after the start bold becomes bold. But note that now the words over the dog have become bold, even though neither of the users wanted to mark those words as bold. The users wanted to change some bold formatting in the first three words. They didn't want to touch the last three words of the document at all. So now we've got this really weird artifact where suddenly the entire rest of the document has become bold because of the change that we made somewhere at the start of the document. And we think this is really bad behavior, but there are actually CRDT libraries that behave like this. But we didn't want to use this in Automerge, so representing rich text as markup is also out of the window. Okay, let's try a third attempt. let's just try to keep it really basic and attach formatting information individually to every single character. And that sounds really inefficient, but maybe we can find a way of compressing it to make it efficient again. So let's not worry too much about that. But let's say that, for example, if we want to have the word the fox jumped with the word jumped bold, we have a bold bit on every single character of the word jumped. And that seemed reasonable. That way we have now indicated exactly which characters are bold and which are non-bold. There's no ambiguity about that. But the problem is, well, we want to support not only bold and italic, but we also want to support things like inline comments. And so inline comments, like in Google Docs, you can select some text and then hit the comment button and then add a comment in the sidebar. And so let's say in this example here, user A wants to add an inline comment to the words the and fox. And maybe they ask the question, which fox, or something like that. And independently, the user B inserts the word brown between the and fox. Now, this inline comment, we also somehow have to attach to every single character. And so, okay, like in this case, it's not just a bit or a single bit like bold or italic, but there has to be maybe a comment ID, and we attach that comment ID individually to every single character within the comment span. That kind of works, but now if we merge these things together, well, characters in the word brown did not have a comment attached to them at the time when the user typed the letters BROWN. So now when we merge these together, we have the with a comment to attach, the word brown with no comment attached, and the word fox with a comment attached again. So we've split the comment into two non-contiguous pieces of comment. And oh god, this is kind of messy, and yeah, whatever, what would we do? We could kind of paper over it by saying that if there's a gap in the comment, we render it as a single comment anyway. But on the whole, like it just seemed like this wasn't really the best representation either. And so finally, we moved to the fourth attempt, and this is the actual representation of rich text that we use for this peritext algorithm, and which is now also implemented in Automerge. And the idea here is that we represent the actual text of the document as just plain text. No formatting appears anywhere inside the flow of the text. But outside of the text, externally, we can attach annotation spans to any range of characters. The way this works is that actually internally, every character in Automerge has a unique ID. And so if we want to attach some, for example, bold formatting to a span of characters, we can say attach bold from this character ID up to that character ID. Everything within that span will be bold, everything outside it will not be. Now, it may sound incredibly expensive to have all of those unique IDs for characters, but actually Automerge includes a compression scheme which allows us to maintain that sort of data very efficiently. We probably don't really have time to talk about that compression scheme in this talk, but I do have separate talks that explain how to do that. So you can find those that more detail if you're interested. But so what we have now is the ability to say from some character ID up to some other character ID is bold, and we can also just attach a timestamp to that bold instruction. And let's say in this example now we have the text, the fox jumped, and the entire text is bold. And let's say that user A wants to unbold the second and third words, but leave the first word bold. And so the way we now represent this is not by deleting the bold operation. The bold operation just remains there. That's in fact useful history, because if we want to look back at what the state of the document was yesterday, then actually it's quite handy to just have the old operations there anyway. Instead, what we do is we generate an additional unbold operation with a timestamp T2, and the timestamp T2 will be later than the timestamp T1, and this tells us that for the word fox and jumped, the unbold should override the bold. So those characters should then be bold, even though they are within, the characters in fox and jumped should be non-bold, even though they do appear within a bold span, but that bold span is overwritten by a later unbold operation. And independently, the user B might mark the word jumped as italic, and again, that's just saying from this character ID up to that character ID is italic with timestamp T3. And now these operations can be merged in a really easy, really straightforward way. And that is, for each span of characters, we look what are the set of operations that apply to that span of characters for character formatting properties that are independent from each other. So for example, bold we consider separately from italic, which we consider separately from text color. And so for each of those properties, we handle things independently. For operations that change the same property, like bold and unbold, well, we just pick the one with the highest timestamp. And for different properties, they can be merged independently. And so in this case now, we've split up the document into these chunks of contiguous characters, where the word the is bold, the word fox is non-bold, and the word italic is non-bold and italic. The word jumped is non-bold and italic. And so we've got sensible merging behavior, and this merging behavior really arose from the way that we modeled the data in the first place. And that just shows how much of a difference it makes whether you model the data as a tree or as markup or as a list of individual characters with per character annotations, or in this case, annotation spans attached externally to the text. So those are exactly the kind of design decisions that we think through while implementing Automerge, so that hopefully, if you want to build this kind of collaboration software that includes some collaboratively editable rich text somewhere, you don't have to think about it, because the algorithm is just implemented in the library and you can just build upon that. So that is the idea. Hopefully Automerge can be this foundation for building cross-platform collaborative apps on top of a single data model library, a single data model, which is this JSON with a few extensions, such as rich text. And you can underneath have whatever storage and networking layers that you like. That's really all I have time to talk about for today. So I suggest we move on to Q&A, and here are just a few final links if you want to look up any further details. So thank you very much, and let's have some questions.
All right. Hey, Martin, that was awesome. The audience has so many questions for you.
Okay, great.
I have been trying to sort of collate and coordinate all of these. And I'm going to try and move around, because we've got questions that are technical and extremely specific. We've got wide open questions about philosophy. People want to know so many things. So, okay, let's start here. And actually, forgive me for saying this, but I just want to point out, because they're not listed on this slide here, but Jeffrey Litt and Sarah Slim Lim were the collaborators on the Paratext paper.
Yes.
Who are the lead authors actually on that paper, and they're just not on this slide. Since you spent so much time on Paratext, I wanted to make sure we gave them a shout out.
Yes, sorry that I missed this, but they are on this slide.
Oh, good. There they are, yeah. So actually, I think let's start by talking a little bit about conflicts, because people ask a lot of questions about this, and we're going to get to the highest voted things as well, but let's start there, because I feel like it trails off nicely here. People, are hearing all about your kind of conflict resolution strategies and how to tell if there is a conflict. But I think two things that are coming up a bunch of times are like, how do you make sure that the conflict resolution is good, right? Like, what if the automatic resolution isn't actually useful? And two, which is like, what if you don't like what the automatic selection is? Can you go back and do something different? Can you make different decisions? Can you talk a little bit about that?
Yeah, great questions. So this is also something that we worried about a lot in the early phases of Automerge, and that is actually me and Peter together with people from the Ink and Switch research lab, built a whole series of prototypes of collaboration software, partly with the goal of exploring exactly these kind of conflict resolution things. So, there's graphics software, there's note-taking software, there's project management software, and a whole bunch of different things we built there. And what we realized in building those prototypes is that actually the conflict resolution behavior is surprisingly rarely a problem. And part of the reason for that is that actually users are intuitively quite good at avoiding conflicts. And so if you're working on an article, then often people will do things like say, oh, I'm working on the introduction section, please don't touch that. You can work on any of the other sections. And so that means that the actual conflict resolution machinery is very rarely actually exercised in practice, because most of the time the users just naturally informally coordinate out of band in order to avoid those conflicts. Of course, the library still has to handle the conflicts, because there has to be some backstop there, but actually that backstop is invoked fairly rarely. The other part of that is that in many cases, a simple conflict resolution protocol is totally fine. So let's say it's graphics software, and there's a picture on a slide, and one user dragged the picture to this XY position, and another user dragged the picture to a different XY position. And what should the behavior be there? And you could say like, oh, okay, well, it's a conflict because we can't automatically resolve this. The picture can either be in one position or the other. We can't have both positions at the same time. So we've got to show the user interface to the users and get them to resolve it manually to decide whether the picture should be here or there. But actually, it seems that in most cases, users don't care that much. As long as everyone has the picture in the same place on their slides, it's just fine. And if the picture is not where you want it, then just fix it up, drag it to the place where it should be in the final state. So actually, the cases in which actually difficult conflict resolution happen seem to be quite few and far between. Now they do happen, and so you could imagine, for example, say it's a calendar event.
Let me give you a problem.
Okay, yeah, give me one. Yeah.
What if I'm a journalist writing for the New York Times, or maybe what if I'm a copy editor working for the New York Times, and I want to make sure that the journalists aren't accidentally slipping any unverified facts or claims into print on the Gray Lady?
Right. Yeah. Yeah, and so this is something that we've looked at quite a bit, and it's in this case it's less about the merge behavior and more about having control about what the final document looks like. And so you could actually regard merging behavior as one instance of this, where you want to make sure that if some automatic merge happens, you can review the result and make sure that the result is what you wanted. But that also applies generally with changes. If somebody made a change to the document, you want to be able to review the result and make sure that the end result is what you wanted. And so for this, the fact that Automerge tracks any changes that are made to the document actually comes in incredibly handy, because we can use that same mechanism that is used for conflict resolution. We can use that same mechanism to enable version control like things. So we can, for example, look back at how did the document change between yesterday's version and today's version, and show the user an exact diff of precisely what changed. And this drops out of Automerge in a fairly easy way, because we're already tracking all of those changes anyway. So it's then just a matter of representing those changes as a diff view somehow in the application. So actually the user interface is kind of the hardest part of that, but the data structure allows these diffs to be computed very well. And so that way, that then kind of provides a good final answer to the merging behavior question, I think, which is that, yes, in some cases, it might be that the automatic merge is not what you wanted, but as long as the application makes it easy to review the state of the application and see how the data changed from one version to the next, then the users are still in control, and the users can be sure that the final document represents their wishes. So that's why we haven't worried too much about the details of like weird manual merge conflict resolutions. You can manually merge a conflict if, for example, two users update the same property of the same object. Automerge just retains all of the values that were written to that property, and then you can resolve them manually if you like.
Okay, let's switch to talking a little bit about data in the large. Obviously, as the author of Designing Data-Intensive Applications, you have a pretty broad base of knowledge about different data systems out there. Several people asked questions, and in fact, the highest voted question is one about, well, let's call it medium data. It's not quite a big data question, because it's pretty easy to have more data in a database than you could fit on your local drive. Well, what do we do if there's too much data to download right now to answer whatever question you have?
Yeah, that's a really interesting challenge for local first software. And so what we started out with Automerge is focusing on small data, you might call it. Like it's deliberately small. It's the data that a user or a small team of users might create through their own input. And there's only so fast how users can type on a keyboard or draw objects on a screen. And so the amount of data that you can accumulate in a text editor or in graphic software or something like that is not that big. Really, the way how you get big files is by having binary assets like images from a camera or videos or things like that. They are big, but the actual human inputs, like the edits that the users make to those things and the vector graphics and so on, they tend to be small amounts of data where it is feasible to just download it all to the user's device.
Okay.
Now, there is definitely this in-between space where, say, it's the wiki from a large company, and so that might be enough data that actually you don't want to download the entire wiki contents to each user's local device. And so in that case, it would make sense to have some sort of servers that allow you to, for example, search through the wiki using a server-side index rather than having to download everything. So
well, kind of, oh, sorry.
Yeah.
I was going to say, bouncing off of there into another popular question, several people asked, first, what happens if the server never comes back? And sort of along those lines, what is the role of the server as an authoritative source? Is a server authoritative in this model? I mean, we're used to sort of this, the Postgres database knows everything, and then we ask it questions. How do we think about both servers coming and going and the role of sort of centralized systems?
Yeah, the way we've been thinking about local first software is that we try to avoid authoritative servers if at all possible. And so that means really leaning into this idea that users might edit things independently and then everything is resolved through the conflict resolution. It means there are certain things you simply cannot do. Like if you're selling seats in a theater and you want to make sure that you don't have two different users booking the same seat in the theater, that's an example of like some physical resource that you've got contention on. So that I would represent just with a traditional server-side database. I wouldn't do that as local first software because in that case, you actually want to ensure that two users don't book the same seat. But on the whole, for the kind of applications I told about earlier, this left-hand column sweet spot of file editing type things, in that case, we think actually you can get away without an authoritative server. And so, for example, you might choose to have multiple servers. You might have servers from multiple different providers and sync through whichever one happens to be available right now. And they might even be federated so that you sync from server to server. They can all speak the same protocol across any of these connections. And the CRDT doesn't care. All the CRDT needs is some way that if one user makes an edit, it somehow ends up on the other user's devices. It doesn't care whether that goes through a single server or multiple servers or a peer-to-peer network or whatever. And so that just gives us a huge amount of flexibility in terms of the data synchronization infrastructure we can use here.
Well, great. I'm going to pivot off that. Somebody asked whether you can do peer-to-peer networks, and your answer seems to suggest that you can. Similarly, people want to know, like, is this fast? Does the sync mean you have to send around a lot of data all the time? Could you run this fast enough to do sort of a live multiplayer game at 60 hertz or that kind of synchronization? Like, can you use WebRTC or do we have to use a WebSocket? Does Automerge have opinions about that?
So peer-to-peer is fine. From Automerge's point of view, it doesn't care. You can use peer-to-peer, that's no problem. There are lots of practical problems in making peer-to-peer networking work reliably because you have all the problems with NAT traversal, hole punching, getting through firewalls, linking together users who are on the same Wi-Fi but firewalled off from each other, like you often get with guest Wi-Fis in cafes or things like that. So there's a lot of problems on the networking layer there of actually making peer-to-peer networking work reliably. But from the Automerge point of view, peer-to-peer is totally fine. You can use that if you like, or you could use some hybrid of both peer-to-peer and server-based, and just if one of them fails, fall back to the other, for example. I think that would be quite a good compromise. In terms of your question on performance, and like, can you use this for high-performance apps? So with Automerge, the way it currently works is it tracks the full editing history of a document, and that's typically what you want in sort of file editing use cases where you want version control. You want to be able to see what changes did your colleague make yesterday. It's perhaps a bit high overhead for a game, where in a game, maybe you would want to replay a game session later and see, what states the game went through. It's conceivable, but it's also conceivable that in a gameplay, actually, any state that's not the latest state you just want to throw away. And so I would maybe not use Automerge necessarily for that kind of game where it's very ephemeral state, but you can definitely use it for sort of low latency collaboration. And so, text editors where when you type a single keystroke that appears immediately on another user's user, or like drawing apps where one user's pen strokes from their
Perhaps
tablet.
a board game or other kinds of games like that where you don't have so much hidden state, or where it's more interactive and lower sort of ephemeral volume. You might want to see that history. That's interesting.
Yeah, you could imagine it for that. So we've designed it less for games just because our focus has been these kind of productivity apps and file editing style apps. But I think there's some other people exploring CRDTs for games. I think that's quite an interesting space as well.
One question that's shooting up the ranks here actually is that you said that you need to synchronize time across different machines. Now, I know what that really means, but lots of people out there are thinking to themselves, aha, you can't really synchronize clocks on different computers. So how does this work, Martin?
You caught me out. No, I'm enough of a distributed systems person to never trust a clock. Any kind of wall clock time that comes across is always treated with very high suspicion. So Automerge stores wall clock timestamps for any changes that it makes, but it actually uses those for nothing. The only purpose that they have is so that if you want to visualize the changes of who edited what when, then you have some indication of when to go by, so that you know if a change happened yesterday or today. But of course, that will only be correct if the clock is correct, but otherwise the timestamp is not used for conflict resolution. I did mention timestamps in the context of the rich text algorithm, where I said, for example, the unbold has a higher timestamp than the bold. In that case, they're actually logical timestamps, so they're not actually wall clock timestamps at all. They're actually just counters, basically. And so for that reason, clock synchronization is not a problem there. So the algorithm is correct even with no clock synchronization whatsoever.
Great. Okay. So people have been asking this for a while, and I'm putting it off to build the anticipation. But obviously, you mentioned in your opening that you study end-to-end encryption, but you didn't say the word encryption, I think, a single time in the entire talk. People are also really interested more broadly than that about data security policies, ACLs, roles, etc. Do you want to say a few words about that? I think that's probably going to be about the end of the time we have here. So,
yeah, I mean, that's.
If you answer quickly, I can do one more.
Okay, so that's a whole separate talk, basically.
Yes.
I do have a whole separate talk on that, even several. The encryption.
Are those talks available online anywhere?
Some of them are, I think. I'd have to look where, though. I don't remember off the top of my head.
I'm sure that we can send around something in the notes afterwards. If you've got some of those things, we can share them. And also, I'll say for everybody in the audience here that the Automerge project has a website. It's automerge.org. We also have a GitHub profile, github.com/automerge. And there's a community Slack where if you were interested in this stuff and would like to follow up, you're very welcome to come. And Martin hangs out there, as well as some of the other Automerge developers and users, and we have a community. So if you're really interested in hearing more about this or looking more at it, there's plenty of details there. And I would say this area of kind of data security policies and end-to-end encryption is an area that's actively under development and study.
Exactly. And so you can take lots of different approaches there. So for example, as the simplest, you can just do your authorization and authentication on the server and just do a traditional web app thing. And that works fine. But if you want the end-to-end encryption, well, then you need ways of evolving the encryption keys. For example, so if a user gets removed, you want to rotate their keys. One protocol that we've looked at for that is MLS, messaging level security, which provides this kind of group key agreement. We also have our own protocol, which is more decentralized. So MLS actually relies on a central server. We have our own home design protocol, which is fully decentralized while still being quite efficient, which is called DCGKA.
Martin, I'm going to jump in, sorry, because we're in our last minute, and I wanted to make sure at least people asked a bunch of questions about Google Wave and other existing technologies and so on. Very, very quickly, can you just explain the difference between a CRDT and OT and how it kind of fits in that landscape?
Yeah, so Google Wave and Google Docs, etc., use operational transformation, which is a different family of algorithms compared to CRDTs. It kind of achieves the same sort of goal, but through different means. We think CRDTs have a bunch of advantages, including being able to run over peer-to-peer networks, for example, which is something that operational transformation has struggled with. So it gives us much more flexibility in terms of the networking topology.
I just saw the clock tick over. I'm so sorry, everybody, if I didn't get to your questions. Please feel free to join us elsewhere on the internet for more follow-up. You can chat more here at on.acm.org. There'll be an email sent around with slides and more links. Thanks so much, Martin. I really enjoyed the talk myself, and it sounds like the audience found it really provocative and sort of inspiring. Thanks to everybody who came and asked questions and participated in the chat. It was a really lively session, and thank you so much. The talk will be online at learning.acm.org in a few days. You'll also be able to see announcements for upcoming talks and other activities there and at acm.org. Please take a moment to fill out the survey, which will come around, and you can suggest future topics or future speakers. So on behalf of the ACM, Martin, and myself, thank you so much for joining us, and we hope you join us again in the future. And that's the end of this talk.
Thanks for joining us. Bye.